Good morning, all. And today we'll be discussing about something known as strange metal. So basically, this is a special kind of metal. We'll be discussing in more details uh, as you go ahead. So, oh, sorry. Yes. So this is how we'll go forward. Fermi liquid theory and quasi-particles. Then high DC superconductor, particularly cuprates, and then strange metals, and followed by some unsolved isotopes. Now, so this is what it is. Yes, this is the introduction. So you know this has been a recurring theme in the condensed matter physics. So always you discover some material and then classify it by considering some of its very unique physical properties or characteristics, and then try to explain it. And if we cannot explain it with existing theory, then come up with some new models or theory. Model I mean to say, because as far as the magnetism is concerned, we have only microscopic theory we have at present, particularly in superconductivity, that is BCS theory, which is a microscopic theory and which can predict some unique physical property and has been verified over the years. So all the phase transition are belongs to actually Landau paradigm. We all know that it provides the bedrock for understanding all the metal we are acquainted with so far. And very recently, you know, this paradigm has been proven to be wrong one or falsified, or is not at least applicable to the one special category known as the topological uh, materials. We know wild semi-metal or Dirac semi-metal along that line. And another thing very recently people have found, which is known as strange metal. So what is strange about it, we'll discuss in more details. But you all know and very much familiar also, the concept of quasi-particle arose with the description of a Landau theory of spontaneous symmetry breaking or phase transition, you can call. I mean to say, if you consider a very simple example of a copper wire and a current carrying uh, conductor, and elementary question people often used to ask, what is it that carries the current? So we all know it is electrons. It is a textbook definition. However, considering its interaction with the nearby lattice and nearby electrons, or people call it quasi-particles. It does possess the feature of particles, but in addition to that, it has some more to it. In what so to say, the effective mass. We know the charge and mass of an electron is pretty are fundamental constants. However, the mass of the quasi-particles are not fundamental constant. However, it is otherwise known as effective mass. So this is very this is one of the incredible theory or proposal given by Landau and explain almost all the physical properties of the metals. And moreover, sorry that I could not see something. Sorry that. Can you see the screen?
I can see your Chrome web.
Google page. Chrome web.
Can you?
What are you trying to show now?
I can
Yes.
see resistivity plot of metal and
No, this one. I think I messed up with something.
now it is content.
Yes, this is where I was. This is where I was, right?
Yes.
Okay. So that's what is the concept of quasi-particles. Why I'm telling this in a more subtle way? Because we'll see how all of these things have been violated in the material where we are going to name it as a strange, and not we, people have named it. So then the saturation of resistivity, you all have seen the resistivity of a metal. So this is how it is. So if suppose I have a normal metal like copper, as I said, or silver. So this violet color plot is nothing but the resistivity of a metal. You can see, okay, which is very much familiar to with the Matheson rule, the some non-zero resistivity at a zero temperature, which is associated with the defect and the impurity, and followed by some electron scattering. Here there are two very unique features. One is at low enough temperature, or so to say at a zero temperature, tends to zero, not zero, it tends to zero. And similarly at a higher enough temperatures. At a low temperature, you can see it shows the tendency of saturations. And that saturation tendency is associated with the quantized lattice vibration get frozen out as you go down the temperature. That's why this saturation tendency is showing up here. However, if you go higher the temperature, there is a criteria called Mott-Eiff-Regel criteria. Mott-Eiff-Regel criteria, I mean to say, physically, let's suppose an electron is propagating in a current carrying conductor, and basically where does that resistance is originating from? It is originated from the scattering of the electron with the nearby electrons and the lattice vibration at a given temperature. But if you keep on increasing the temperature, the vibration will be more turbulent lattice. Then electron also possess more kinetic energy, so scattering also will be more. But at the same time, if energy is more, then sometime you will reach a condition that the mean free path of electron will be order of the lattice constant, and at that condition, it can reach this criteria or reach this condition, and experimentally it will be evident from the saturation tendency of the resistivity plot of a material, particularly metal, at a higher temperature. This is the two unique feature. One is known as MIR. We'll discuss it. I have mentioned this high temperature saturation is associated with MIR limit, they call it in short, and the low temperature is the quantized lattice vibration frozen out. Now, but if you look at the superconductor transition, this is you have the first superconductor people used to call an niobium, or what is it called? At the liquid helium temperature at 4.2 Kelvin. So this is why this is called pure superconductor transition, and almost 10 to the power minus 5 ohm centimeter resistivity. But here you please give your attention at a higher enough temperature, resistivity plot of both superconductor, and this superconductor, to be specific, it is a BCS type. Okay, and this is a normal metal, which is explained both the theory microscopically can be explained by taking Landau paradigm into consideration. But you can see at a higher enough temperature, none of these plots show linear variation with the temperature. They are not linear. They are different polynomial dependency, but they are pretty sure are not linear in nature. Okay, this is one feature. Now, in addition to that, this Landau formula theory also explains many particle interaction. Where is the many particle interaction? Superconductor, you can see that at least 2 electrons you need to form a copper pair, and there are many of them in order to make the system really free from scattering, and then make the electron to flow very smoothly. And then heavy fermion system like samarium hexaboride, or a system like that where quantum physics have been investigated, that also can be very much explained in terms of Landau theory. This is in short was the success story of the Landau paradigm. The typical feature in the Landau theory is concept of quasi-particle. Wherever there is a flow of current, there is a concept of quasi-particle. Why am I repeating it quasi-particle, quasi-particle? Whenever you are describing the propagation of energy in terms of particle, you are actually dealing with locality. So this thing you'll see it is no more followed with a special kind of material, and that's why it is known as strange. The concept of the violation concept of quasi-particle or locality is no more valid in a particular situation of the matter. And the beauty in 1986, Benroj and Muller, they found the high tissue superconductor in lanthanum-based cuprate, La 2 minus X BAX CO4. LABA, they call it LBCEO, the system. And then nobody has ever come up with a successful microscopic theory to explain what is the mechanism at the microscopic level or atomic level uh, of this phenomena. And the people have been trying really hard enough. In fact, many people have already given up that probably this was under the umbrella of a BCS theory, but BCS theory could not predict this much high temperature superconductor. At present, today, the high TC superconductor transition temperature is around 143 K, 130 K at ambient pressure. Remember, whenever you are discussing about superconductor, please make sure that what is the condition of pressure. That is more important because people have come up with transition temperature which can exceed up to room temperature, but that is at extremely high pressure, like hydrogen fluoride, hydrogen sulfide, or some specific kind of material with very huge pressure. They can possess a very high temperature. Though it is very much interesting for academic purpose, but as far as the practical application is concerned, for which superconductivity is really an incredible field of research, doesn't really fulfill the requirement. Okay, so now this is what, sorry, this is what it is. What is the motivation? Motivation is since 1986, almost it's how many years? 35 years gone by. More than 1 lakh papers have been published on superconductors. But that's what literature says at least. None of those papers have come up with a satisfactory explanation. How come some cuprate? Cuprate means CO for, I will tell you, to give you a feel, this is the formula. You see, this is copper oxide is there, no? So that's why they call it in short cuprate. Okay. So this cuprate, how come these systems or this family of systems actually possess that high transition temperature, but Cooper pair mechanism doesn't hold good there. Nobody, even today, nobody understand it. It is an open problem. That's why I have written the statement of motivation there. It has eluded the physicist for about 30 years, but almost unanimous verdict or acceptance across the globe. This is probably the mechanism behind it. No, sir. And another feature I have mentioned here, you see at the higher temperature region, you don't see this is linear in nature. But here, you will see, particularly enigmatic in the normal state from which superconductivity emerges, so much so that this phase has been dubbed as a strange matter. Why it is strange? I have already explained you. In normal matter, the propagation of current happened due to the propagation of quasi-particles, and the particle nature prevails. But no such thing holds good as far as these systems are concerned. Example is this. You see the resistivity, and this is, you can clearly see it is superconducting transition at a very low enough temperature around 15K, 14K. Okay. What you see, it's very much linear. Okay. So, but previously we saw this is Baring-Cooper's Kuiper superconductor. You don't see that linearity. And one may ask, why this linearity has to do with strangeness. What is so special about this linearity? This linearity indicates Landau theory is no more valid. The same thing happened in 1985 when von Friesen discovered the integer quantum Hall effect. There was no concept of spontaneous symmetry breaking. They could not explain it by invoking the Landau theory. That is why the completely new different field emerged, what we now know today as a topological phases of the matter, and the transition belongs to the topological phase transition. Okay. Now, let us distinguish and let us pinpoint what is so special. The most
Can we-
fundamental, yes,
Can you please go back to the previous slide?
yes,
So in this slide, you have taken PR, which is praseodymium.
yes, you are right. Praseodymium, cerium, copper oxide.
Okay, so will this material be still called as cuprate if you change these elements? So I think
Yes, yes,
praseodymium is from F block element.
you can change all these praseodymium and cerium with all the rare earth elements.
Okay, you mean F block elements.
Lanthanum, neodymium, niobium, all those things.
Okay, okay, and cerium also.
Yes, yes, because you can see that X now one rare earth replacing another rare earth.
Mhm. So is it true that only a particular pair will work? So for example, praseodymium will only work with cerium and will not work with other element. Is it that?
It's not like that. Actually, it is all about you have to see the whole purpose was, you see, how did they get here? Actually, they were trying to find a system where the transition temperature will be high, because that is what the whole purpose of condensed matter physics stage. Let us find out the superconducting transition at temperature very close to the room temperature, where we can make the best use of this.
Yeah, true. Okay.
In the process, they got it. And while you are actually preparing a system, you have to take into some specific criteria. I mean to say, there are called solubility limit. And another thing is, since this is oxide based compound, you have to consider that the metallicity has to be there. And the biggest problem with the oxide compound is these are insulators. These are insulator. But what you are dealing with, superconductor. You are actually trying to find a system inside or in a family of a insulator which is superconductor, and with a specific combination only you can come up with you can successfully manage to. That is one thing. And second thing is, make sure you do not actually produce the secondary phase, because the moment you produce the secondary phase which is magnetically active, magnetism and superconductivity doesn't go hand in hand. It will kill. So at least these two important feature one has to take into consideration. Make sure you always produce or synthesize a single phase material, so that it is better to study, better to predict, and better to control.
Okay.
Because if I have a single phase, because magnetism is all about the propagation and polarization of spin, nothing else. In an atomic level, it is only the arrangement and polarization of individual spin. Let's suppose if there are multiple spin and those spins have different environment, then I cannot have control in my hand. I cannot control it the way I want. Is it not? Let's suppose in a system, a long range magnetic order is there. Let's suppose iron. Iron, the moment you hit it above 1041 K, you can demagnetize it. It is no more magnetic. But imagine if you have iron and cobalt. Okay, so cobalt has a transition temperature around 1300 K. So if you just go above 1000 K, you think that your system become demagnetized. It's no more magnetic, but your cobalt is still shows magnetism.
when you combine it with iron.
Yeah, no, I'm telling individually.
Okay.
Suppose you imagine there is a iron. If you ask me what is the Curie temperature of iron, it is 1041 K.
Okay.
Cobalt has a transition temperature around 1300 K or well above that. So let's now imagine I have to prepare an alloy, iron cobalt.
Just one clarification. So when you say transition, you mean Curie temperature?
Yes.
Okay. Okay.
And that transition, whatever you are telling it, martensite transition, it will take a lot more temperature to make it that sort of transition. Structural, you are talking about, if I am correct.
So when you combine them, what happens then?
So if in a system I have a multiple magnetically active element, and I do actually scan over a range of temperature. So at a particular temperature, I may presume that, oh, this element has a Curie temperature this much. So since I have exceeded it, I have already exceeded the temperature of that limit. So probably the system has become non-magnetic. However, the other magnetically active element which transition temperature is yet to arrive is will still show some magnetic feature or not.
Okay. Okay. Okay.
So that is when the ultimate purpose of this material synthesis is to come up with a device form so that it can be useful. And if I cannot have a single handle, or if I cannot actually have a control and predictive power, so how can I make the best use of that material? I cannot.
Okay.
So that is why, as you said, that's the very important point. You have to come up with a very specific combination of these elements with proper stoichiometry. You see, you can ask why x is equal to 0.5, 0.16, or 0.15, 0.16. Why not it is 36335? Is it not? This is x value, that doping. So if you do so, you may end up with the secondary phase.
If you change x too much.
Okay. You may end up with structural distortion. You may end up with additional phase. You may end up with some multiple complex magnetic phases where superconductivity will completely cancel out.
Oh, okay. Okay.
Because magnetism doesn't like superconductivity and vice versa. Na?
Meissner effect.
Yes, very much.
Okay.
So you have to actually, in fact, I will show you. Maybe that time idea will be more clear. So here actually how we are going to tune this resistivity. In short, this resistivity depend on what factors. So of course with one temperature, another which is doping concentration, another which is magnetic field. I'll show you that.
Okay.
So let us first clarify and how does it different from the normal metals. It's a well-defined quasi-particle feature is no more available there. So even today we are not sure. If you can ask me, in a strange metal, see, let me explain here itself. So you see, this is the superconducting transition. Can you see this one? Okay. Hello, am I audible?
Yes.
Yeah. This is superconducting transition. So after superconducting transition, let's say after 20 K, what is this? This is metallic state. This is resistivity of a metal. I have shown you here. Okay. This is superconducting transition. What is this? This is metal, right? Because you can see this feature is very much similar to the metallic behavior, or not? But only difference is that linearity was not there in viscous type of superconductor, what cuprate superconductor possesses. So this linearity here violate the concept of quasi-particle nature. So if you ask me in short, what did that carry the electric current here? I have no idea.
Okay.
So
if I understood it correctly, can I just confirm one thing?
Can I repeat?
Can I just confirm one thing, whether I've understood it correctly or not? Please. Okay, so if you have quasi particles, then it will not show linear behavior. So and that behavior has been studied a lot, but in this case we are getting linear behavior. which cannot be due to quasi particles. So, and we don't know what is causing this linearity.
Let me add you something. You are very much correct, but partially. I mean, I thought I think I should add some more information here. I told you this gets saturated, right? At
Mhm.
least it shows some tendency of saturation at a T tends to 0. And here also at a higher temperature, it also shows the tendency of saturation. If you go na, it also will show that. I told you one, this is due to the quantized lattice vibration, I mean phonon. So it gets frozen out here, right?
Okay.
That's why this low temperature saturation behavior came into picture. However, at a higher temperature, when your mean free path actually is of the order of lattice constant, then you can show the tendency of saturation. So you first tell, then when I'm talking about the electron phonon interaction, how can I at least intuitively imagine without considering its particle nature into account? It is not possible, right?
I have one more question. When one thing is when temperature becomes large, why do you call or why do you say that for normal metal it saturates? Because as I can see, it sort of increases linearly when you increase temperature. Why do you call it as
I,
saturation?
no, here the plot what I have shown here, na,
Mm-hmm.
it doesn't show, but there are other. If you go much higher temperature, it will saturate.
Okay.
Here in picture, I beg pardon. Here it has not been shown within this limit. But
Okay.
at a low temperature, you can clearly see there is a tendency of saturation.
Okay.
However, yes. So they call it MIR limit, the Mott-Eiffel limit. That's in mathematically KL less than equal to 1. Fermi wave vector, mean free path less than equal to 1.
Mm-hmm.
So here, so what did you say? You said, okay, if this linearity in resistivity has been shown up experimentally, is it an evident that quasi-particle feature is no more varied? Indeed, this is the case. Had it been not the case, it would have shown the tendency of saturation. People have investigated up to 1000 Kelvin, but they haven't shown any tendency of saturation. But in metallic case, if you go to 300K, 400K, you will get the saturation.
Okay.
In some metals.
Okay. And one more thing.
Yes.
Because I remember that I read in maybe some 12th class. I don't remember when, but I remember that this rho, the resistivity increases linearly with temperature. So and so this linear dependence is for what sort of materials? So maybe my understanding is not that advanced, but this is what I remember.
You are very much correct, but there is a small caution line below that. Maybe I do not know whether you have forgotten. It is of a particular temperature.
Mm-hmm.
That you are talking about a formula rho equal to rho 0 plus alpha t. Is it not?
Yes.
So that alpha is a linear thermal expansion coefficient.
Mm-hmm.
So you have to make sure that alpha is very small. So if the alpha will be very small, means alpha is what? T minus T0 by T0.
For a given material, it's a constant. It depends upon the nature of the material.
Obviously, that's what I'm telling. That means how we are calculating that T minus T0 by T0, na? Linear thermal expansion coefficient.
Okay.
So that alpha as a function of first power of T is valid only up to a specific range of temperature. It is not the formula for all the range of temperatures.
Okay.
Did you get my point?
Okay,
up to a certain range. So up to, since it is a textbook, I don't know whether they have been mentioned it there or whatever it is, but this is valid for a particular temperature. And as you said, that is also another point, that particular temperature is not same for all the materials.
And so when you increase the temperature, higher order powers will come. T square,
Yes.
T cube, T power 4.
You are right. That's what make it saturate.
Okay. Saturation, but polynomial never saturates.
I mean,
Polynomial function never saturates.
That's another very good point. Again, you are inclining towards mathematics, but I have a limitation as an experimentalist up to what temperature I can measure, na.
Mm-hmm.
So it will show because scattering will be very high if you keep on increasing the temperature, because the lattice will vibrate very turbulent in a very turbulent way. Electron also will vibrate in uh, mm, vibration will be more. So
Mm-hmm.
that means again resistance will be very high, na?
Mm-hmm.
That's what I mean. The tendency of saturation means that means there onwards you don't see any tendency of metallicity. The resistivity will more or less will get increased.
Okay.
I
Okay.
mean here Rahul bhai, whatever you are telling, there are technique. I think it would have been correct if we would be discussing it in the blackboard. So here you see, I'm telling you this is the linearity. But if you zoom it, can you think it is linear? It is increasing, right?
Mm-hmm. Mm-hmm.
Likewise, as you are telling, now you got my point. Whatever you are telling, that is correct.
Okay.
But with a specific range of temperature up to which an experimentalist can perform the experiment. Because another important thing you have to make sure, you have to actually scan the temperature up to a range where this stoichiometry has to be maintained. Because if you exceed more than the disintegration temperature of this material, you may lose the oxygen.
Mm-hmm. Okay.
That time you may investigate this feature more clearly, but your material is no more same.
Yeah. Okay. Got it. Got it. Okay.
So mathematics side you are correct, and this is our means experimental way of looking at the thing.
Okay. Fine. Thank you.
So and this is one thing, and you can see yes, Mott type Regel limit. Okay, so the most famous is T linear resistance that persists from nearly zero. So although there are several proposed explanations for the strange metal phase, including marginal Fermi liquid, quantum criticality, and the Planckian dissipation. These are three different phenomena people have proposed, but it has not been actually satisfied the urge or requirement of the people. So that is why none of these proposed phenomena is universally accepted even today. So that's why people are calling it an open problem. Another important thing is that yes, this is this thing high TC superconductor, the material, and another important thing you see in BCS theory, this TC is low, but in cuprate superconductor, this TC is high. This TC is high because I told you, 143 you see normal material, no saturation, but in linear in T and a higher TC. So high TC superconductor, where this resistivity is high, but had it been normal metal, how it would have varied? After superconducting transition occur or takes place, next is normal state, is it not? See, in that normal state, resistivity should vary as a square of the temperature, quadratic power of temperature. But in strange metal, it varies linearly. So that is why though people have no idea what sort of mechanism can be invoked or account for the high TC superconductor, they are now attacking the problem from the other side. How about actually knowing the mechanism, why this linearity in resistivity as a function of temperature is coming? And if we can manage to understand it correctly, probably we can understand what sort of mechanism can be account or invoked for the high TC superconductor. That's the uh, game in the town, you can say. That's why this problem has been taken extremely seriously nowadays, strange metal. And it has again become more fancy. Even string theorists also have attacked it from the ADS CFT that duality, you know it from the gravity side. So that is why they are calling it this Planckian dissipation. I told you a mechanism called Planckian dissipation. Planckian dissipation, you know that this is the faster dissipation or a maximally scrambled state. That is the maximum rate at which particle can exchange energy. So they call it, as I was mentioning, Subir Sachdev from Harvard. So their group have proposed that probably the very similar kind of thing is happening inside the black hole, and they also found three constant: Planck's constant, Boltzmann constant, and I think HKB, and I think black body radiation Hawking formula is C, I think, right? All right. H cross G and C. I think similarly, three fundamental constants are associated with this, and they are also claiming there is one-to-one correspondence between the strange metal and black hole, provided you have taken into consideration the ADS-CFT duality. That is the string theorist approach to strange metal behavior in the high TC cuprate superconductor. Now you see, this is the schematic. You can see this is the temperature and this is my doping. Generally, this the material what I have shown as an example is an antiferromagnetic insulators and a Mott insulator. And you would have heard about various types of insulator. Let's suppose carbon and diamond. It's a band insulator. Anderson insulators are there. Mott insulators are there. Topological insulators are there. Mott insulator, Kondo insulators are there. This insulator, Mott insulator, is due to the insulating behavior in the system occurs due to the strong electron interaction, strong correlation between the electrons. And you see, if you first it is in antiferromagnetic insulator state, then you start doping, you'll find a pseudo gap formation partially overlapping of the orbitals, and then you'll reach a superconducting state. Rahul, you are asking one question. So with a particular temperature, you can only get the superconducting dome. Can you see this?
Mm-hmm.
At a particular doping concentration, that X equal to 0.15, 0.16 we were discussing, right? So for random substitution or doping, you cannot have superconducting transition.
Okay.
And then if you dope it excessively, then you may end up with the Fermi-liquid usual Landau paradigm thing. But in between these two, in this particular doping concentration, just above superconducting region lies the strange metal feature. That's why, yes.
So it looks that this is this circular in shape. This SC dome is this circular in shape?
It is not. Other side, I have no idea how to probe other side.
No. My question is that does this curve follow some sort of pattern? Like, for example, this boundary is represented by a circle, so that there is some sort of relationship between temperature and the doping. That will satisfy the equation of a circle, for example.
I think that railway I have to look at, because in other thing people have actually given the distorted set. It's not exactly the spirit to the hemisphere what you can see here. It's a schematic gap plot.
Okay, fine.
But in order to infer that conclusion, I have to actually list out to many experimental evidence, and then if I can put them all together, I can have some opinion on that.
Because finding this sort of curve will be very hard, because you have to just change the I mean, you have to vary the doping, and then you have to see at what temperature, above what temperature the material loses its superconductivity.
Yes, you're right. Yes, it's very hard to do. That's why I said in some other ray diagram I have seen people have shown some distorted this image, distorted superconducting region. It's not as circular. So that's why if I can put at least 100 or 200 samples and put them together and see how they actually vary.
Exactly.
Then only I can tell you some something on this question. Okay. Now, so what we have found here, the concept of quasi-particle no more, here the T linear resistivity and a very much similar kind of feature has also been observed in magnetoresistance, measurement of resistivity in the function of resistivity as a function of temperature in presence of magnetic field, and that is from 20 Kelvin down to the millikelvin range. And you see the magnetic field up to 65 Tesla. See, one question you can ask: 65 Tesla is quite a strong magnetic field, is it not? So if you do apply that much strong magnetic field, how come it is not affecting the transport behavior of any metal? Because I am pretty sure uh, if you put a copper wire or silver wire under extremely high magnetic field, let's suppose it carries a current, and they put it in 65 Tesla, 80 Tesla, 90 Tesla. So it certainly affects the behavior of the current and indeed the transportation feature of the carriers which conduct electricity, isn't it? So that is also another surprise. How come this magnetic field of this strength hardly has any effect on the linearity feature of the resistivity? That's one question. One thing we have, many people have obtained from the experiment. Another thing is this T-square behavior. See, here we saw there is a T linearity in the resistivity in N type of doping. In P type of doping, in P type of doping, in N type of doping, you may sometimes find T-square resistivity, and that is up to 1000 Kelvin, which is not obvious and not expected as far as the conventional metal is concerned, which follow the Landau theory of phase transition or Fermi liquid. That's another finding. And it is very much confirmed that probably the particle picture breaks down. No local entity carries the current. So these are three and in fact, people have studied the specific heat. People have studied the uh, thermal conductivity, entropy, and they found there is no one-to-one correspondence, and it is extremely difficult to reconcile the feature with the material which obey the Landau Fermi liquid theory. In every aspect, it differs significantly from the conventional metal features. That is why they call it strange metal. Though, as I have mentioned, people have come up with some theory, Planck's dissipation, this marginal Fermi liquid, quantum criticality, but none of them would actually explain it satisfactorily so that people can accept it across the globe. So to say in short, this still is an open questions. So, to list out what are the issues associated with this, what is the origin of the low temperature linear in T resistivity, and how does the magnetoresistance remain a linear function of H down to the low enough temperature. And this feature in N type and P type doping, they do have different temperature dependency. And is it really the violation of Moore-Frege limit? None of this question has been addressed so far. It is an experimental finding. What I have discussed, it is only the experimental finding, and people could not actually explain it by using usual Fermi liquid theory. Again, if you try to be specific, one can ask further this question. And to me, it sounds like a more ambitious project than this. I think if one can find the answer to this question, slowly one can understand the question mentioned above. So as I mentioning, the term refer to resistivity behavior of a correlated electron system, high or low temperature. So you can ask. So one question: suppose a copper wire carrying a current. Easily one can answer the same quasi-particle or electron which carries the current in the conductor at a high enough temperature is very much responsible for the propagation of current at a low enough temperature. It is very sound like obvious, but it is not the case. because as I have explained you that the tendency of saturation and why do they saturate at a different temperature regime is way different. Likewise, we do not know. First of all, particle picture breaks down. Quasi-particle feature is no more applied here. If that is not the case, is it necessarily the charge carrier, which is responsible for the high temperature propagation, is equally responsible for the low temperature? We have no idea. Likewise, does it that T-linear resistivity, people are calling it is a Planckian dissipation. Planckian dissipation is the fastest way to dissipate the energy to the surrounding, or is it something else? Like Martinez, but the fourth one, if you see, has it anything to do with propagating degrees of freedom? If you remember the information paradox of the black hole, and how did Bekenstein and Hawking derive that entropy formula? How many number of degrees of freedom one black hole can have is essentially associated with the area, and thereby it is associated with the entropy. But if you remember our usual class of thermodynamics, entropy is always associated with its volume, because you know the number of degrees freedom enclosed in a given volume. But that is not the case with the black hole. It is associated with the area, and that is why people often used to call colloquially, if two black holes actually merge one another, its area increases. They never used to call if two black holes actually merge each other, their volume increases. They call it their area increases. Likewise, since it is associated with the microscopic degrees of freedom, and we have no idea what is that microscopic degrees of freedom which carries the current in the metallic state in the Cuprate superconductor after transient temperature happen. Probably this also can give insight how to proceed towards quantum gravity, or vice versa. If we can come up with a theory of quantum gravity, we may actually borrow some idea from that and probably try to use that idea and explain the strangeness feature of the Cuprate superconductor. So the field is wide open, and it's exciting. People have been working around the globe, but it is very new. And let's see how much time it will take to come up with some satisfactory explanation. So with this, thank you for your attention.
Thank you, Gandhi, for your talk. So,
Thanks.
does anyone has any question? I have asked my questions already.
No, I don't have.
Okay, and Nikhil, you?
I don't have a question regarding that strange metal, but I just want to ask one thing.
Yeah.
And when in normal metal, you told na that in high temperature, when mean free path is approximately equal to lattice parameter, it is saturated. Resistivity is saturated.
Yes.
What is exactly the reason? Like if it is somewhat equals to the saturation is happening, means the scattering is not happening anymore. Additional scattering.
No, you have understood otherwise. Actually, you see, resistivity is nothing but the hindrance to flow. Is it not?
Yes.
And in normal metal, whatever resistivity curve we have derived or people have mathematically written down, it is based on the electron-phonon interaction into consideration.
Yes.
And if you look at the curve, let me show you this one. Can you see, Nikhil?
I can see.
Yeah. So you see what I am telling, it is tendency to saturate.
It
You
is
can
low
call
temperature.
it. Yes, low temperature. What does it mean? You have actually arrested all the lattice vibration. That's why I have told you the quantized lattice vibration has been frozen out. So electron is no more scattering with any lattice vibration.
No, sir.
Sorry.
No, I am asking about the high temperature where that fluctuations are. Okay.
I'm coming to
that. Okay.
Yes. So here, here you see the electron which is actually carrying the current or quasi particle, so to say, is no more bumping on each other with the lattice, because lattice means ion nearby doesn't vibrate that frequently, because you have almost arrested that lattice vibration. Apart from 0 point fluctuation, there is no finite temperature here. It is almost a zero temperature, I'm telling. T tends to
Hmm.
0. So you have arrested the lattice vibration, and electron also are not flowing that randomly or that violently. So in principle, if our assumption is correct as per the Fermi liquid theory, it is the electron propagation per unit second across the area held perpendicular to the direction of the propagation is the right definition of current. Then we should not have gotten any resistivity here anymore, because in principle it is not getting scattered from any nearby elementary particles. Is it not?
Yes.
So where is it coming from? Why there is a finite resistivity? It is coming from the impurities. We are calling that rho zero, which doesn't depend upon temperature anymore. It is already inbuilt. Is it not?
Yes.
Coming to the higher temperature, you see, higher temperature means your mean free. How does mean free path vary with the temperature? Mean free path is the path traveled by an electron
Between the collision.
between the two collisions. If your energy is more, electron is moving really violently, quite randomly. Even lattice ions are also vibrating very frequently. The probability of getting scattered is very much probable, na?
Yes,
Or not?
it is.
So if you remember the X-ray, how come X-ray is acting as a diffraction plate for the lattice is acting as a diffraction plate for the X-ray? Because you know that
Because it
the
is
X-ray wavelength is of the order of
approximately
lattice parameter.
Hmm.
Now, did you follow what I tell?
Yeah,
Understood?
in the same way, this is similar.
Yes, that has to be the order of lattice constant. Then only it will get scattered seriously, na? Hello?
I
Nikhil?
got it that why it is scattering means it is approximately in the same range, but
Yes.
saturation means that the somehow the number of scattering or the proportion which electrons were getting scattered is getting same even if we are increasing the temperature still.
No. Here they're different. Here the low temperature saturation is coming out of impurity associated with the material. High temperature saturation is coming out of because of lattice vibration and mean free path.
No, the
Did you
reason
understand?
reason I got means
Yeah.
the reason is different for the both regions, right?
Yeah. Yes.
Okay, I will go through it and then I will ask.
Okay.
Maybe I am somewhere I am mistaken.
Okay.